Welcome to Maths with EJD. In what I can see as the last video for coordinate geometry, I'll be looking at coordinate geometry meets calculus. Let's look at the marriage between coordinate geometry and calculus. In its very essence, coordinate geometry itself is a marriage between algebra and of course uh geometry, right? So here, we also see calculus coming into the mix, and that's what we are considering here. Previously, we had been talking about things like tangent, slope, and all that. And these are things that are related to calculus. So let's go ahead and see what this holds for us. So coordinate geometry meets calculus, the learning goals and roadmap. By the end, you'll be able to interpret slope of a curve as a derivative because the whole idea of dy dx is changing y over changing x. And changing y is like y2 minus y1 over x2 minus over changing x, which is x2 minus x1. That's in essence a slope, which is a derivative. So you can see slope is derivative. So that's a very nice meeting between coordinate geometry and calculus. We can write tangent and normal equations for explicit, implicit, and parametric curves and solve optimization problems involving distance, area, and geometric constraints, and visualize key ideas using Python. The roadmap is we see slope as a derivative, talking about secant, moving to tangent, then tangent and normal for y equals f of x, including edge cases. Edge cases are the points where calculus misbehaves, right? Then we have implicit curves like f of x comma y equals 0. If you look at my playlist on basic calculus, you discover we talk about implicit function. Those are functions that cannot be separated, where the dependent variable x and independent variable y cannot be separated. That is, you cannot clearly express y as a function of x. Basically, that's what an implicit function is. And we have parametric curves where the both the independent variable x and dependent variable y are expressed as functions of a third parameter, say t or theta or whatever you want to talk about. And then we have optimization, which relates to distance and area. Things like shortest distance to a point. Optimization is all about getting the best of every solution, of every situation. So you want to, you're driving from a warehouse to retailers. You want to see, and there are many routes, right? You want to go through the easiest route for sure. So that's the idea of optimization. Then we can have some reasonable Python utilities and practice. Well, I think I want to delete this last one. I think it's not necessary. So it's more like what we did in the last video where we talked about some kind of automation. So I think it's not necessary to bother about that. Okay, so we have that. So let's go straight to the first part where we talk about slope as a derivative, where we see secant going to tangent. So for y equals f of x, slope between x naught, f of x naught, and x naught plus h, f of x naught plus h. See, these are 2 points, not like our normal x1, y1, x2, y2. So we have the slope, slope secant, that's like f of x naught plus h minus f of x naught here, all over x naught plus h minus x naught. So x naught cancels out, so you just have this h. That is by definition, that is derivative. So now if we now look at derivative in terms of instantaneous slope, that means we have f prime of x naught, which is now the limit as h approaches 0 of this expression up here now. All right. So the interpretation is that the tangent line at x naught is the best linear approximation of the curve near x naught. That is what that is about. Okay, so we can see an example of that right here, where we have an example involving slope at a point. So we want to do both symbolic and numeric to see how that goes. Okay, so in that case now, we have if f of x is x squared plus 3x minus 1, and of course f prime of x is 2x plus 3, differentiate x squared, you get 2x, differentiate 3x, you get 3, differentiate 1, which is constant, that's 0. So at x naught equals 2, if you take x naught to be 2, we have f prime of 2, that'll be 2 times 2, 4 plus 3, that's simply 7. But we can also do numeric sanity check. So if you do that here, so you're basically saying something like f prime of 2 will now be f of 2 plus h minus f of h all over h. So so this is just it right here. Because don't forget f of x is itself is x squared plus 3x minus 1. So f of so let me I guess I need to go to the worksheet now. F prime of 2, like we said, is f of 2 plus h minus f of, is it f of 2 now? I think it's f of 2 all over h, okay? And don't and from what we have from that page, let's see. Yeah, f of 2 plus h minus f of 2 all over h. So f of x is x squared plus 3x minus 1. f of x is x squared plus 3x minus 1. X squared plus 3x minus 1. Okay? F of x is x squared plus 3x minus 1. So in that case, now we simply have f prime of 2 to be f of 2 plus h now simply means we have 2 plus h squared plus 3 into 2 plus h minus 1. Okay, we have the whole of this minus f of 2. That's 2 squared plus 3 times 2 minus 1 all over h. Of course, we are taking that as limit h approaches 0, limit as h goes to 0. So then we can expand all that. So f prime of 2 is, when we square this now, we can be smart about that. That's 4 plus 4h plus h squared plus 6 plus 6 rather, not 6h, plus 6 plus 3h minus 1. And then for this other side, we have minus 2 squared, that's 4 plus 6 minus 1 all over h now. Limit as h approaches 0. So we have f prime of 2 going further to be, so 4 plus 6, that's 10, plus 4h plus 3, that's 7h, plus h squared. Okay, this should actually be 4 plus 6, 10, minus 1, that's 9. Okay, this is 9 right there. So 4h plus 3, that's 7h plus h squared. Okay, minus 4 plus 6, 10. 10 minus 1, that's 9. So this is minus 9 right here, all over h. So minus 9 cancels 9 straight up. So we have f prime of 2. That's limit as h goes to 0 still, don't forget. So this is limit as h goes to 0. So that is 7h plus h squared all over h. Okay, things are getting tidier now. So f prime of 2 is simply limit as h goes to 0. We have 7h over h plus h squared over h. Okay, so f prime of 2 now is equal to limit as h goes to 0 of 7h over h is 7 plus h squared over plus h in short plus h. Now we still have h after dividing through. So f prime of 2 is simply 7 plus 0 and the answer is 7. So like the original one where we got 7, this one is also 7. So the two of them align like that. So you see when we did the direct one here, just differentiate and substitute directly, we get 7. If we also do this one, we get 7 also. So then we can code that in Python. I won't bother so much about that. And see what it gives us like that. Okay. So convergence of second slope to derivative. We have this right here. Okay. So having done that, we move on to tangent. We move on to tangent and normal for y equals f of x. So you see, given that given y equals f of x, and then points, we now have a point which is x naught comma f of x naught. So this is as good as saying x1 y1 like we've always said previously, but for this situation I will just use this. So we have tangent slope as mt equals f prime of x naught, right? And the normal slope, so tangent slope is mt, the normal slope, as f prime of f prime of x naught, right? Then the normal slope is mn equals the negative inverse of this, because the product of two slopes that are, the normal slope, the normal to this tangent will actually be perpendicular to it. So there are two slopes the product of the two slopes must be equal to -1, and mt must not be equal to 0, right? So that's why the normal slope will be mn equals -1 over mt. So we now have equations like this now. You have tangent y minus f of x naught equals f prime of x naught into x minus x naught. That's the equation in that case. But for normal, it will be y minus f of x naught equals minus inverse of this. That's 1 over f prime of x naught into x minus x naught. So those are the differences. So only the slope is different, basically. So if you can have edge cases, so if f prime of x naught is equal to 0, right? So that is the derivative is 0. Tangent will be horizontal. So y is equal to f of x naught. And the normal is vertical, where x is equal to x naught, because the slope is undefined. So if derivative doesn't exist, tangent is undefined, and we have a cusp, a corner, or a vertical tangent. Okay, so let's take an example, like an example 2. Tangent are normal at a flat point. Let f of x be x cubed minus 3x squared plus 2. Then f prime of x surely will be 3x squared minus 6x plus 0, because this is constant. So we have 3x squared minus 6x. So at x not equals 2, so put 2 in there, you have 8. I mean, if you put 2, f of 2 will be 2 raised to power 3, that's 8, minus 3 times 2 raised to power 2, 4, that's 3 times 4, 12, and plus 2. So you get minus 2. 8 minus 12 is minus 4 plus 2. That's minus 2. Then for the derivative, if you put f prime of 2, you have 3 times 2 squared. That's 12. 6 times 2 is also 12. That's 0. Then the tangent now. See that the slope tells us about the tangent. So the tangent y is equal to minus 2. Okay? The tangent is minus 2, and that will be horizontal, while the normal will be x, that is vertical in that case, right? So um so we have this minus 2 like this, and because the derivative at 2 is 0 now, so it means that it will be the normal will be vertical, because the f prime of 2 is undefined, is 0, so the slope will be undefined. Now let's go. So we can then plot tangent and normal for a general point using the same thing we did there. So you can check out the code doing all of that stuff. Okay, so you see at x equals 2, there's a kind of problem around here. So it approaches it, but it doesn't really get there. So this point P is actually 2 comma minus 2. And we have the tangent, which is in orange. The normal to the tangent is this blue dot, which is at 90 degrees with it, like we saw up there. Then let's talk about implicit curves like f of x comma y equals 0. And when we talk about implicit curves, right, it's a case where it's difficult to make y explicitly a subject of x, right? So implicit curves f of x comma y equals 0. If f of x comma y is equal to 0 and the f dy is not equal to 0, if you differentiate and you don't get 0 near x naught y naught, then dy dx will be minus f of x over f of y. So the tangent slope, unlike what we had before, the tangent slope empty to be minus f sub x into x naught minus y naught all over f of y into x naught minus y naught. The normal slope mn is equal to minus 1 over m2 if m2 is not equal to 0. So imagine a circle, for instance. Say you have x squared plus y squared minus 25 equals 0. This is a nice example of an implicit curve, right? So you have the whole thing equal to 0. So differentiate this with respect to x. That's f sub x now. You get 2x. Y squared is seen as a constant because x is focused. 25 is also constant, so it goes to 0. So f sub x is 2x. Then f sub y is 2y, right? And that means that dy dx, as we know already, is minus f of x over minus f sub x over f sub y. So that's minus x over y because this is 2x over 2y. So dy dx is minus x over y. So at 3, 4, the tangent slope empty is minus 3 over 4 because this is 3, this is 4. So it means that the tangent will be y minus 4 equals minus 3 over 4 into x minus 3. And for the normal slope now, to just be y minus 4. So this minus 3 over 4, the negative inverse of it is minus 4 over 3. That's simply 4 over 3. So this is the equation of the slope, of the normal. So we can even visualize all of this. For instance, this is x squared plus y squared minus 25 equals 0. So x squared plus y squared minus 25 equals 0. That's a circle with radius 5. Okay, so we now have a tangent to that. That is y minus 4 into 3 over y minus 4 equals minus 3 over 4 x minus 3. Okay, y minus 4 equals 3. Is it 3 over 4 minus 3 over 4? Yeah, minus 3 over 4 equals minus 3 over 4 into x minus 3. So you can see it's at the tangent at 3, 4 right there. Then for the normal, so it's the same thing, but the slope changes. So that'll just be y minus 4 equals negative inverse of minus 3 over 4 is 4 over 3 into x minus 3. So you see, it's at perfect 90 degrees to that at the same 3, 4. So the normal is perpendicular to the tangent. That's the idea right there. So that's the kind of thing we have here. Desmos has done it for us, but this is another picture of that. So the circle is x squared plus y squared equals 25, or if you like, x squared minus y squared, x squared plus y squared minus 25 equals 0. Same thing. Then you have the point of tangency, that's 3, 4, and the tangent is this line, while this is the normal at the same 3, 4. Now let's talk about parametric curves. So if x is equal to x of t and y is equal to y of t, and x prime of t is not equal to 0, that is the so as far as y x prime of t is not equal to 0, x prime of t is the x the t, because that's what we have down here. So it means that dy dx is equal to dy dt over dx dt. That's how, this is how that goes, right? You have for parametric curves, x equals x of t, y equals y of t. See what happens. You have x equals x of t and y equals y of t. So dx dt, so that's so you have okay, dy dx in short, because each of the variable is a function of t. So dy dx will be dy dt, all right, divided by dx dt. So you are dividing by this. So that's why it must not be equal to 0. So that means that dy dx now is equal to dy dt times, okay, well, I think a better way to put it is this, dy dt all over dx dt. So, and dx dt must not be equal to 0. If not, the derivative will be undefined, right? Very important to take note of that, okay? So once we have this at t equals t naught, then the tangent slope will be m sub t, which is y prime of t naught all over x prime of t naught. That's substituting t naught into all of this. And the tangent line at p is x naught, y naught equals y minus y naught. And that is equal to mt into x minus x naught, like this. Of course, if you want the normal too, so just take the negative inverse of this. So imagine an ellipse where we have x equals a cos t and y equals b sine t. Okay, so you see that x prime of t will be equal to, if you differentiate this with respect to t, that'll be differentiate cos, you get minus sign, so that'll be minus a sine t, and y prime of t is b cos t. So dy dx will be minus b cos t over a sine t equals minus b over cos over sine is cos t. That's the dy dx. So you can then substitute whatever t you want to put that right there. So imagine that our a is 4.0 and b is 2.0. All right. If we have that, then and we have our t naught. T naught is an angle pi over 4, that's 45 degrees. And then we now have x naught, y naught to be a cos theta, b sine theta. All right. All of that. A cos theta, b sine theta, like we defined up there. So dx dt, we have all of this. So we just use everything we have up there, except now that we have 4 and 2. And then we do this and we see the ellipse. You see the ellipse now has this. So we have the ellipse, and then the point on ellipse is this point of tangency. So tangent at t naught, that's the orange one. So again, we can have tangent angle. Let's talk about tangent angle, normal angle, and orientation. So talking about tangent angle, if slope m of t equals tan theta, then the tangent angle is theta, which is arctan of m of t mod pi, right? Then the normal angle is theta plus pi over 2 mod pi. The orientation from a parametric curves, the direction of increasing t gives the arrow of traversal along the curve. The tangent vector is then x prime of t, y prime of t. Now let's talk about optimization and general strategy. Now, I'm particularly, I love optimization. My master's degree was into optimization and optimal control. So I like to talk about optimization a lot. Okay. So for optimization, right, you are looking for the best way to get things done, the shortest way to arrive at a place, the smallest amount you need to spend, the maximum profit you can make. You are minimizing costs, you are minimizing negative things, and you're optimizing positive. Yeah, you're maximizing positive things. That's the idea of optimization. So define the target function Q, whether it's a distance or area, etc. in one variable. Then determine feasible domain. That's geometric constraint. That will require differentiation, right? So you then differentiate, that's q prime of x. You equate that to 0, you get some critical points. Then you can classify this critical point via second derivative of geometry, then interpret solution geometrically. Now, to get a clearer picture of this, you can check applications of differentiation in under my basic calculus playlist. Okay, so geometric normal condition here, that's distance to curve, for instance. So we may want to see things like, okay, we may have something like this, that at the nearest point, on a curve to an external point, right? The line joining them is normal to the curve, something like that. So let's imagine this works example. So shortest distance from 0, 3 to y equals x squared. So imagine we have 0, 3. Imagine we have point 0, 3, 0, 3. Then, and we have y equals x squared. Y equals x squared. Okay, so we want to look from this point now, you want to find the shortest distance. So you can go from here to here, from here to here, but you want to get the smallest of that distance, basically. So we need a p, right? Which is the x on the x-axis and x squared on this, this curve is x squared. So we need that. So let p be x comma x squared. So the distance squared now, so the distance between x comma x squared and 0 comma 3 will simply be x minus 0 squared plus x squared minus 3 all squared. So using the idea of coordinate geometry that we have always known, then here now you have, if you expand this, you simply have x squared. And when you expand this, you have x raised to power 4 minus 6x squared, this one now, then plus 9. So you have x squared, x raised to power 4 minus 6x squared plus 9. So this x squared from here is what you have right here. Then you can tidy things up. So you have x raised to power 4 minus 6x squared plus x squared, that's minus 5x squared plus 9, like this. So careful expansion will yield this, that x squared minus 6x squared plus 9 plus x squared is the same thing as x raised to power 4. Okay, we've done this already. Minus 5x squared plus 9. If distance is to 0, 3 via x minus 0 squared plus x minus 3 all squared. Equivalently, we have x squared plus x squared minus 3 all squared. And that is that expansion. So anyhow you do it, you get the same x raised to power 4 minus 5x squared plus 9. Okay, so that's the distance, the square of the distance. Now that you have got the square of the distance, so you can differentiate now. d dx of the square of the distance, it will give us, differentiate this now, you get 4x cubed minus 10x. 9 is constant, so we can factorize 2x. So we have 2x into 2x squared minus 5. So if you equate this to 0, it means 2x is equal to 0. That means x is equal to 0. Then 2x squared minus 5 is 0. So you have 2x squared equals 5. That's x squared equals 5 over 2. Then x is plus or minus square root of 5 over 2. So x is 0, x is plus or minus 5 over 2. So if you evaluate d squared now, so you can now say at x equals 0, so d squared will be, this is 0, and you have 9. So at plus or minus square root of 5 over 2, d squared will be, so you have d, that's x raised to power 4, that's 25. That'll be square root of 5 over 4 raised to power 4. So that means if you square it, the square root is gone, right? And plus or minus will gone, it's gone. So you square again, you have 25 over 4 minus 5 into, then another square here, you square it again. That's square root of plus or minus square root of 5 over 2. If you square that, you have 5 over 2. So that's 25 over 4 minus 5 into 5 over 2 plus this 9 that is constant. Then you can tidy all this up, you get 11 over 4. Okay? Those are critical points, in this thing. So then you can then find minimum at x equals plus or minus square root of 5 over 2. So you have the points now. You have, so in this case, don't forget, we have this x and then x squared. So plus or minus 5 over 2 and then 5 over 2. So we can, let's plot that point and see what it looks like. So we have square root. Okay, we don't need this. Square roots, okay, of 5 over 2, comma, 5 over 2. So you see that's that's the shortest, that's the point on this curve. Okay, of course we can have another part of this, right? So we can have this, it's plus or minus. This is the plus part now. The minus part can just be this. So it's either this point or this point. So the shortest distance from that curve will be this or that, right? Plus or minus. So we have the label like that also. So that makes sense. So normal condition check, you can then check the normal. So at x equals root 5 over 2, f prime of x is 2x equals 2 root 5 over 2. That's root 10. Line from 0 to 3 to x squared has slope. So it has this slope minus 1 over root 10, which is the negative reciprocal of root 10. So it's a normal. So we are good to go. That's normality check now. So everything we've done there now. So we just run the code right here. Okay, I mean, this is the distance squared now. So this is the square of the distance right now. Okay, I can actually make this appear in LaTeX format. I just put dollar signs and run this. So it looks better. It's nothing has changed. Has it changed? Nothing has changed. Where else do we have that thing? Okay, there are many other places where we have all this. So I can do this. Dollar sign. Does it change? Should. Yeah, now you see it looks better. This one is still here. Where is it now? From, okay, yeah, this particular one. I can put dollar sign and that works. Yeah, everything is tidy. So distance squared. So if this is the distance squared to 0, 3 now. That's from y equals x squared. So we have this whole thing like that on the distance. But then the actual thing, like you can see, we have y equals x squared is the curve. So you have the external point 0, 3, like that. The nearest point is either this or this. The nearest point on the positive side is this, is the orange one. On the negative side, it's the green one. And then we have all of that. Okay, normal nearest point, that's this yellow point on the positive side. Nearest point on the negative side is the green one. Then the segment is the dotted line in orange. That's normal segment positive. Normal segment negative is the dotted green line. Okay, and that tallies with what we have right here. Okay, so now we need to find. So imagine we want to find maximum area rectangle under y equals a minus bx squared. That's in the first quadrant. So let upper right corner be x comma y on the curve with x greater than or equal to 0 and y greater than or equal to 0. And y is minus bx squared. So in that case, now we know that ax would be a of x rather, okay, would be x dot y, okay, which is x into a minus bx squared because, this is y, right? So because we're looking for maximum area of rectangle under y equals a, so it's area of rectangle is just length times breadth. So we have y. If we had specific numbers, maybe I would have visualized this, but it's okay. So we have x into a minus bx squared. That's ax minus bx cubed. So if we differentiate a prime of x now, so this is the area of the rectangle, like we already know, which is length times breadth. So we have a prime of x, that is differentiate ax, that's a, differentiate bx cubed, you get minus 3bx squared, and equate that to 0. That implies that the critical value of x now, if you solve all this now, will be square root of a over root 3, square root of a over 3b. So it's only positive, no negative, because we're talking about area. We can't have negative area. It's not like the other one that we did. So then it means that y star now will be you substituting this value. So we have a minus bx star squared. So that's a minus b into a over 3b. When you square this now, the square root is gone. A over 3b. So b cancels out. So at the end of the day, you have a minus a over 3b. All right. So that's 2a over 3b. Like that. So this is like a over 1 minus a over 3b. So that's yeah, so yeah, I mean b is gone, right? So a over 1 minus a over 3 rather. So you have LCM is 3a minus a, that's 2a over 3. So the maximum area in that case would be x star y star. So x star is square root of a over 3b, y star is 2a over 3. So it gives you this whole 2a raised by 3 over 2 all over 3 root 3b, like that. So you can have a special case where you have 8b, 8b, like that. 8b. I mean, a is 8, b is 1. So if you put that here, then I can maybe plot this now. So that'll be 8 minus x squared, like that. So I can do 8 minus x squared. So imagine that we have y is equal to 8 minus x raised to power 2, like this. So with this now, I want to get the optimal values of x star and y star. So that's root 8 over 3 and 16 over 3. Root 8 over 3 and 16 over 3. Okay. So that's square roots of 8 over 3, comma, 16 over 3. So you see this is the best value of x and y around here. So when we talk about area, so that's how that goes. Okay. So this code takes care of that idea using the special case of 8 and 1. So just like what you have right here. So as you can see. Okay. And then maximum area under rectangle, is something like this now. So I can write this better to be x squared looking neat. So I can just do this dollar here, then dollar here, and then that's a latex thing to do. So you have this right here. Okay, let's talk about shortest distance from x1, y1 to line ax plus by plus c. So shortest distance from a point to a line, that's basically what that is about. So distance formula, so it is derivable via calculus of projection. We have d to be absolute value of ax plus by plus c, all over square root of a squared plus b squared. Now we came across something like this when we're talking about the locus of points, always equidistant from two intersecting lines, something like that. So the calculus outline is such that we have you minimize d squared to be x minus y1 squared plus y minus y1 squared, subject to ax plus by plus c equals we're using Lagrange multipliers. The solution is the perpendicular on the point to the line. So it's more like the same thing, like the angular bisector of the angle between the intersecting lines. The angular bisectors, because we have more than one of such angular bisectors. So, I mean, we'll just do the code for this. You can go through and see. So imagine you have this line going, and then the shortest distance from this point to this point. Of course, you can have this distance, you can have this distance, you can have all kinds of distance, but this is the one you have, which is the shortest. So, and that is the line 2x minus y minus 4 equals 0. So you have point P, you have the foot F, and the shortest segment is this PF, if you like that. So that's how, so talking about a line, right? So you have 2x minus y minus 4 equals 0. That's the line. and then the point is 2. So 2x minus y minus 4, we can do that here. 2x, right? 2x minus y minus 4 equals 0. That's the equation of the line. And then from the point minus 2, if you take the point minus 2 comma 3, so that's minus 2 comma 3 comma 3. So the shortest distance from this to that now is what this is about. So that's what this one has given us. So that happens to be this. Okay, do we know the analytic foot of perpendicular? We have all this. Okay, can I read out? Can I get the line from here? Foot, we have a squared plus b squared. Okay, that's the whole computation going on like this. That's the whole computation right there. And then, okay, we are not able to get that directly. So, oh, we can. So this is the distance right now. We get it, that segment. So that can be obtained, working with this whole expression like that. That talks about the distance. Okay, so having done that, we can look at some edge cases and diagnostics. Edge cases are cases where diagnostics, where derivatives misbehave. So if you can have a horizontal tangent where f prime of x naught is equal to 0 and tangent y is equal to f of x naught in that case, then, so once the derivative is equal to 0, then the tangent is simply equal to f of x naught. Then for the vertical tangent, the limit of f prime of x as x approaches x naught is equal to plus or minus infinity. It is not representable. So as y equals f of x near x naught, then you can have corners and cusps. So left and right derivatives differ or blow up, no tangent. Like a very good case is the case of maybe tan x, so that as it approaches 90 degrees, it blows up. It doesn't ever get there. So that's some kind of edge case. Then you have implicit failures. If f prime of y is equal to 0 at a point, implicit derivative will be minus f of x over f of y. So, and that breaks because f of y is equal to 0, so this cannot work. So you can parameterize or swap rules. Then you can have parametric stalls, like if x prime of t naught is equal to 0, which is equal to y prime of t naught. So you have higher order analysis required in that case. In the case of parametric, because you're dividing by dx dt, you should for x equals x of t and y equals y of t, dy dx is actually dy dt over dx dt. If dx dt is 0, then you can't do anything. So those are edge cases, and their derivatives get to misbehave. So we have practice questions like it's my practice, so you want to try out your hands on this. For f of x equals 3x cubed minus 2x plus 1, find f prime of minus 1 and the tangent at x equals minus 1, basically. So to find that, you just differentiate, right? You get 9x squared minus 4x, and then you substitute 1 into it. That'll be like 9 minus 9 plus 4, that's 13. So that's the slope right there. And since you know the slope, and with tangent at minus 1, then you can easily compute that. Find the tangent and normal to y equals root x at x equals 4. So from everything we've said, you can work all of this out. So try your hands on this and let me know your answers in the comment section, either on YouTube or on Facebook. So with this, we come to the end of this video, and of course, most likely the end of this playlist, except there's something else I find out I need to talk about later, or somebody makes a request, as it happens every now and then on this channel. So I'm open to hear you out. All right. Thank you so much for listening. Let me know how helpful this is for you. And if there's something you like me to try out, feel free to let me know. If you have subscribed already, I thank you so much. If you have not subscribed, of course, you don't want to keep missing out on what is going on. So go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can take it a step further. All right. You can actually become a member of this channel by clicking on join. So, if once you get to my my page name, you see join, and then if you click on join, you find 3 levels of membership, which gives you some extra privileges. and then we can interact together. I mean, at the top of their extra privileges that we can have a one-on-one hangout to talk about maths or data science or data analysis or anything, or scholarships or anything I get to talk about on my page. All right. So feel free to let me know about that if if you become a member and you like to hang out at some point. Okay. So ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.